So I'm being told that we had the wrong QR code up initially, so if you scan the previous code, please rescan this one if you have any questions. We'll have the correct code up when we transition into the Q&A period, so if you got the wrong one before, you'll have a chance again. So I'm going to go ahead and get started. Good morning, everyone. My name is Greg Bowman. I'm the Director of the Division of Physical and Cybersecurity Policy in the NRC's Office of Nuclear Security and Incident Response. I'd like to welcome you to our panel this morning, Beyond Guards, Guns, and Gates, Innovative Approaches to Securing Advanced Reactors. Before we get into the presentation, I wanted to start off with some logistics, things you probably heard all throughout the week. The Wi-Fi code for attendees here in person is RIC 2023. Please remember to silence your electronic devices. As you've seen, if we could move forward to the title slide, please. Thank you. As you've seen in other technical sessions, the Q&A portion of the session will be through electronic means for both virtual and in-person attendees. For those of you in the room with us, hopefully you had a chance to scan the QR code, the correct one, but if not, we'll have it up again as we move into the Q&A portion of the meeting, as I mentioned. For those of you joining us virtually, you'll see a tab at the right side of your screen where you can enter questions. Questions from both the online participants and those using the QR code will be added to the same queue, and we'll try to get through as many of them as we can during the Q&A portion after the panelists' presentations. At the end of the session, if you have any follow-up questions for any of the panelists, they'll be available just outside the room, so please make your way to the exits to have those discussions so we can get ready for the next session. Your feedback is very important to us, and we appreciate it if you take the time to let us know what you thought of this year's RIC. Your insights will help us shape next year's program, just like your insights last year helped us shape this year's program. You can provide feedback through the platform by selecting the feedback tab in the session or by accessing the link from the NRC RIC website. Next slide, please. So as we all know, and as was certainly reinforced this week, there's a lot of energy around new and advanced reactors, including from companies developing innovative technologies and at the NRC to ensuring our preparedness for review of applications that in many cases will include novel approaches for ensuring both safety and security. This is an exciting time for all of us. We're collectively thinking about ways of achieving nuclear security goals in different ways than we've done in the past. That includes designs where it's inherently more difficult for sabotage to lead to core damage, better integration of security features like delay barriers into the initial design, and new ways of looking at access authorization, fitness for duty, and cybersecurity. So we have a distinguished panel of experts with us today with broad experience, regulatory, plant design, public advocacy, and research and development. And I'm looking forward to hearing their thoughts. You've all stuck with us through Thursday morning despite what looks to be some better weather today, so I take that as a good sign that you are too. So if we go to the next slide, I'll make some quick introductions of our panelists before I turn the presentation over to them. So to my left is Stacy Prasad. Stacy's a senior security risk analyst in our reactor security branch. Stacy's been with the NRC since 2003, first as a regional inspector and then in a variety of positions at NRC headquarters. In her current position, she focuses primarily on security for new and advanced reactors. Tony Qualentone is the security and safeguards engineering manager for X-Energy. Tony's responsible for developing the physical protection system for the XE100 Pebble Bed reactor facility. Prior to joining X-Energy, Tony worked in a number of different positions, including for DOE and the Nuclear Energy Institute, and he had a 21-year military career with the U.S. Army Special Forces. Thank you for your service, Tony. J.R. Russell is a member of the technical staff at Sandia National Lab. He joined Sandia in 1980 as a test engineer. J.R.'s extensive experience with research, development, test, and evaluation efforts have enabled him to become a recognized subject matter expert in physical security, intrusion detection technologies, and vulnerability assessments. JR is currently developing new intrusion detection algorithms to optimize detection and minimize false positive alarms, even during harsh weather conditions. Ronnie Franovich is a senior policy advisor at the Breakthrough Institute. She works closely with reactor developers, advocacy groups, and policymakers to press for regulatory reforms to satisfy the Nuclear Energy Innovation and Modernization Act of 2019. Before joining the Breakthrough Institute, Ronnie worked for 30 years at the NRC, where she inspected, licensed, and provided oversight of commercial reactors. Our final panelist is Margaret Ellenson. Margaret is the manager of nuclear facility safeguards and security at Kairos Power. She's responsible for developing and implementing material control and accounting, physical security, cybersecurity, and safeguards information protection. Before joining Kairos Power, Margaret worked for 15 years at the NRC in rulemaking, vulnerability analysis, PRA, and material science research. So with that, I'd like to turn things over to Stacy to kick off our panel discussion. Stacy.
Thanks, Greg. Hi, good morning. Here at the NRC, we're focusing on technology-inclusive and risk-informed functional requirements that build on our existing NRC regulations. That's a mouthful. So basically, what we're focusing on is flexibility and innovation in our security initiatives by emphasizing more performance-based and prescriptive requirements. Slide. So staff is proposing new regulations and updating our guidance documents to support these risk-informed security initiatives. The next few slides focus on protection and bounding times. It's kind of a complicated topic, so I'm going to do my best to kind of give you a bird's eye view of what they are before telling you how useful they could be. So our security regulations basically state that a licensee must have a physical protection program that prevents radiological sabotage at all times. To do this, a licensee is required to identify target sets. Target sets are the combination of equipment and operator actions that must function to prevent radiological sabotage. So basically, if you disable target sets, you're going to have a bad day. So a licensee can screen target sets to determine how and what to protect for their site. Our risk-informed review identified a way to implement protection and bounding times for the target set identification process. As noted in the slide, these times were developed to acknowledge that at a specific time there will be additional resources available to provide support as licensees continue to defend against the threat. These times provide reasonable assurance to a framework that considers how many existing layers of defense, safety, and security work together for protection of the site. Slide. So there's a lot of good reasons for this, and you can read all about it in the SECI. It's SECI 20-0070, and that's the technical evaluation of the security bounding time concept for operating nuclear power plants. But essentially, it enables licensees to refine their protective strategies to focus on the most risk-significant target sets while continuing to maintain physical protection of their site. Slide. So all these slides say protection and bounding time. So what's the difference? So essentially, RAP, the reasonable assurance protection time, is a generic time of 8 hours, and SBT is a site-specific bounding time. These times are the amount of time following the recognition of an attack, so the initiating event, and the time additional actions to prevent adverse effects can be taken. So additional actions can mean anything from getting equipment from a different location or having operators freely move around the site to take mitigative actions. RAP is currently included as one acceptable way that licensees can screen target sets, and it's in NRC guidance. Specifically, it's in Reg Guide 576, the physical protection program at nuclear power reactors. Unfortunately, this is a safeguards document, so you won't be able to read it word for word, but the general information for what has been added is included in that same publicly available SECI 20-0070. And security bounding time, same SECI and up for commission vote. So that's not currently implemented. Next slide. So now we're moving on to some rulemaking in case the guidance wasn't quite exciting enough. So the first rulemaking I'll be discussing is the limited scope rulemaking. This is a consequence-based rulemaking that will allow licensee to take some alternatives to certain prescriptive requirements. So you can read the 5 proposed alternatives up on the slide, but basically the rule is saying, demonstrate how your physical protection program provides assurance on low risk profile of exposure radiation in the event of an accident, so a threat, disabling target sets. And if the criteria is met, there's some flexibility on how you can implement for a location of your secondary alarm station, minimum number of responders, stuff like that. So for example, minimum number of responders, the current security requirement states that it should not be less than 10. However, with the proposed alternatives, this could go down to 0 if off-site armed responders fulfill the interdiction and neutralization functions to protect against the threat. If you're a licensee out there today and think these alternatives look promising, but you think it's going to take forever, if ever, if the rule gets published, because these things do take some time, you can utilize the alternative measure process, which is in Part 73, so it's 7355 Romeo. It kind of explains the process in there, or you could feel free to email one of us. And again, the SECI is available for your review. And I don't want to forget that Dennis Andrecutt led this effort, so a quick shout out to him for all the work he put in there. Next slide. I'm sure you heard about this a lot. It's been a hot topic for the BRIC this year. Part 53 rulemaking. The staff's proposed use for security in this rulemaking would establish a new, voluntary, technology-inclusive, consequence-based for a range of security issues, including the programs that you see listed here on this slide. So basically, this is like the previous rulemaking, however, on a much bigger scale in regards to the flexibilities that are going to be provided. So the biggest flexibility and difference for security, at least in my personal opinion, is that this rulemaking is proposing that the applicant can be relieved from the applicable requirements to defend against radiological sabotage if certain consequence-based criteria are met. If they can't be met, the physical protection requirements still provide an optional pathway for licensees that elect not to demonstrate compliance with the more prescriptive requirements in 7355, which is the current physical security requirements. This rulemaking is quite extensive, and a significant amount of work was put into it, so a quick shout out to Bob Beal for leading this effort, and Steve Vitto and Pete Lee for their lead in the security side. but now it's publicly available for your viewing pleasure. So make sure if you're interested in this rulemaking, carve out a few hours or a few weeks. It's super, super long. Note your comments and provide them to us when the public comment period is open so that we can all work together to make this rule as effective, flexible, safe, and secure as possible. Slide. And to give a nod to Chairman Hansen's opening remarks and celebrate Einstein's birthday week, I'm going to add a quote of my own. The only source of knowledge is experience, and by my own, I meant quoting Einstein. So there's a lot of experience in this room and online, and we are encouraging your input and early engagement on all the topics that we discussed here today. Please, if one of these items is of interest to you because you're an applicant considering new technology, or if you're a member of the public with questions or concerns, we do want to hear it. So I am one of the people that reviews the comments for these rulemakings, for better or worse, so I can assure you you're not wasting your time. All comments reviewed are actually considered. Slide. All right, that's all I have. It says my name here on the slide. A later slide is going to give my boss's email information. Feel free to email him first. He really does love emails.
I do love emails.
And I'll pass it back to Greg.
Thank you, Stacy. We'll now turn it over to Tony.
All right, next slide.
Getting there.
Getting there, okay. Until we get there, good morning and welcome. My name's Anthony Qualatone, Tony Qualatone, and I am the Security and Safeguards Engineering Manager for X-Energy. And today I'm going to give a high-level presentation, information on X-Energy's security by design and also the approach that we're taking to establish our physical protection system. I do apologize. The lights are bright, so I'm not going to be doing much eye contact. Next slide. This is just proprietary information, export control. Next slide. All right, security by design. Again, discussing X-Energy security by design this includes several elements, and that one is the XE100 reactor with its inherent and passive safety characteristics. Also talk about the TRISO fuel, the robustness of that fuel, and also the development of our physical protection program. X-Energy, little history, and if I can get this out in one breath. X-Energy is an American nuclear reactor and fuel engineering company. It was established in 2009, so we haven't been around that long, and we are developing a advanced reactor, a Gen 4 advanced reactor that produces about 200 megawatt thermal and also produces high quality superheated steam at excuse me at 565 degrees Celsius. Sorry. And this can be used for various applications and energy applications. Let's see. Next slide. We won't start yet, but as we move forward with the process in different phases of the designs, we're looking at different tools and capabilities to be able to integrate into the physical protection system. We're thinking outside of the box. We are being very creative at integrating technologies and other capabilities into the protective system. Go ahead and start the video. This is a model we use. It's a Scribe 3D. And this gives us a visualization and kind of lays out our thought process on the design. It'll walk us through this is one of the reactor buildings. We can see pipes, we can see hallways, stairwells, rooms. And this is going to be very beneficial when we design the physical protection systems. As the process matures, we'll use not only this model, security model, but we'll also use path trace analysis and a few of the other simulators that are out there, model simulations out there, Ares and maybe Rhino Core. We'll be able to conduct tabletop exercises to show and demonstrate the effectiveness of our security plan, or have to make adjustments or additions or retractions. So walking through again, this goes out to the area. One of the key elements with X-Energy was on the security by design was early in the stage. They made the decision to take the reactor the steam generator, the fuel handling, the transport of spent fuel, whether it goes back into the reactor or if it goes into the spent storage is to make that below grade. So all those systems are below grade. And that is a huge part of our security by design in that aspect. I don't know if it went through it, but it showed the reactor buildings. It's about 7 meters high off the subsurface and an additional 32 meters, 34 meters below grade. I'll let this finish out. It's a great tool to use. Next slide. Here's security by design, the reactor. We're taking full advantage of the inherent and passive safety characteristics of our reactor. Oops, sorry. The security by design was kind of proven through testing one of the national laboratories. With the test reactor, they put two of the most stringent incident possibilities for the reactor, where the passive safety system mechanism kicked in. But in both tests, they took the coolant away from the flow of the core, and they removed the heat removal capability from the reactor. In both incidences, the reactor, the temperature raised a little bit, and then it cooled back down to about operating level, and in the end, the reactor shut itself down. This without any intervention of operator actions or electric inputs or mechanical. There's no active safety systems that are required to shut this reactor down, so it's very safe. Next slide. So we control criticality. We control heat removal. We contain the fission products. It's in essence, we design a reactor that the core can't be melted. Next slide. All right, the TRISO fuel. This is a huge key component with our security by design. The TRISO fuel is a uranium oxycarbon fuel pellet, and it's actually the secret to the way we're going to think about nuclear with the TRISO fuel. It is the most robust nuclear fuel on Earth, and it's because there's literally billions of sub-millimeter particles of the uranium encapsulated in a protective shell. There's 3 alternate layers of graphite and a ceramic. It's a silicon silicon carbide. It contains the uranium, and each one of these particles acts as a containment system itself, retaining the fission product. In one of those pebbles, 60 millimeter size, about the size of a cue ball, there's 19,000 of these TRISO particles. Each one's encapsulated in that protective shell, and within the reactor, there's 220,000 of these pebbles. So. Next slide. All right, and it's just going through the. This is a control mock-up room at X-Energy at our office, developing all the simulations. We're going through we're developing a CAS and SAS simulator. It's going to have all our capabilities that we integrate into the system. Next slide. And so we talked about the inherent and passive safety systems of the reactor. Now we're going to just scratch the surface on the physical protections strategy systems that we're looking at. Like I said, we're evaluating all kinds of technologies, and we're going to make the decision, and it's going to be integrated into that the inherent and the passive safety systems of the reactor. Next slide. So what do we need to protect against? This is a video that's going to show kind of the capabilities that the adversary has that we need to protect against, and it's going to, I hope it's going to wake you up a little bit. We put a little bit of music to it. You can't have an adversary attack without some rock and roll music. So this is just a little bit of a demonstration. Go ahead and play the slide. This is just showing that, you know, adversaries, they've got time to collect the information that they need. The police show up at the scene of their planning cell, and it's detailed information that they've got before they actually, you know, initiate the attack. So this is kind of their planning cell, full model scale of the site, and then the adversaries conduct their attack. And it just shows some of their capabilities: guns, explosives, some of the barriers that they might encounter. And this is all based on present light water reactor. You won't see any response. This is just the adversaries doing what they need to do to accomplish their mission. And this is not safeguards. This is a made-up facility. Going through the different layers, got to get around the site. They've got the information. They know where to go and what they need to do to get there. And in this scenario, they just show that they made it to the containment. This is kind of the modeling simulation software that we'll be utilizing to put our defenses and our protection systems up against what the adversaries are going to be provided with. And it'll show whether the security plan is effective or we need to make the adjustments. Next slide. All right, so in the development of the physical protection system and program, you know, we're looking at all kinds of courses of action, taking what the new rule proposed language is going to be and then, you know, implementing it into those courses of actions. We've looked at the whole spectrum of, you know, whether it's a full armed security force or going down to where there's allowance of, you know, minimum numbers and also even no armed response at the facility, relying on local law enforcement to provide that interdiction and neutralization portion of the requirement. So, you know, some of the technologies that we're looking at to be able to meet the 7355. Next slide. Okay, this is just some of the tools that we've also used in developing our courses of action. It just gives us whether it's going to be, you know, semi-successful or successful, or we need to make adjustments. Next slide. And I don't want to steal RJ's thunder, and I won't. But you know, what we're looking at doing is not making this facility, you know, your grandfather's nuke plant. So we're looking at advanced technologies with the deliberate motion algorithms that JR will talk about, but setting up a perimeter that doesn't even rely on, you know, your standard intrusion detection systems, relying on radar, long-range acoustic devices, laser dazzlers. Next slide. And this just kind of depicts the facility, getting 360-degree coverage, getting the alarm way out, you know, prior to the protected area barrier. And again, I'm not gonna go into JR's information. Next slide. We've also looked at you know, other physical barriers, and this is just a consideration. It's not, you know, anything that X Energy is going to implement. But go ahead and do the flyover video. And this shows X Energy's design facility. We've evaluated the technology. It's called the Metalith Wall. It's a blast barrier. It's 15 feet high by 8 feet wide, able to withstand any kind of blast that's put up against it. No effect on the other side. Although you do blast waves, it'll push over, and about the size of the barrier, it'll dip back down. So you still got to deal with those pressure waves. But that just shows, that capability, that technology, if we were to go down that path. And that's, you can go to the next slide. All right, and we're also going to be integrating technology with AI, robots, drones, facial recognition. We're putting this into a mission planning operation platform where an operator will have command and control of all these autonomous technologies from a single remote display. And he'll be able to control all that information. So we're evaluating all the technologies, and we will utilize what we need to do to make this happen. Next slide. And of course, once there's interior pathways, we're looking at barriers that are almost indestructible. Next slide. These are made out of materials that was tested with 50 cal full metal jacket and also 50 cal slap rounds, which is the Sabotted light armored piercing 50 cal. Could not penetrate this material. And also on the bottom corner there, you see a C4 shaped charge, didn't even penetrate the material. So the goal is to extend that time that the adversaries would need to get into the target area. Hopefully expending all the resources that they have, and then next slide, they resort to mechanical, and it's not happening. So that is X-Energy's proposed development of the physical protection system, and with the integration of the inherent and passive safeties. Any questions? Or I guess
So we'll get to the questions.
Yes.
Yeah.
Yeah.
So I do have one request of the audience. As you're doing your feedback on the RIC session, if you could please nominate Tony to be our music coordinator for next year, I would really appreciate that. Thank you, Tony. With that, we'll turn things over to JR to talk about some of the research.
Do I have the option to speak from the podium so I can
If you
point out?
prefer to speak, yeah, if you prefer the
Can
podium.
we do that?
Do you want my timer?
Just throw something at me. Thank you.
Make sure you get the microphone close to your mouth.
Okay. Let's see. Thank you. And the reason I wanted to be here, because I'm going to use the pointer and point out a couple of things on the slides. I've learned, this is my first RIC conference, and I learned a lot. The first thing I've learned now from this presentation is I need to have rock and roll music in my next presentation. That's
It's the standard now.
Now you tell me. Let's see. So I'm pleased to have the opportunity to share with you a concept we've been working on called deliberate motion analytics. I believe it's an enabling technology for security of the future. DMA is basically a sensor fusion algorithm that we designed to improve detection and reduce nuisance alarms. And it has the interesting side benefit of, I believe, significantly reducing costs for our next generation perimeters. In this presentation, I'm going to briefly give you an idea of what DMA is, what its capabilities are. I'm going to show you some examples of the performance of DMA in different environments. And I'm also going to introduce a new security architecture that's going to be enabled by DMA that I believe will actually improve performance and decrease costs. And we'll talk about that. In one of the previous AI technology sessions I sat in, there were two questions that I'm also going to answer. The first question was, do we think AI can help security in the nuclear industry? My answer is a definite yes. And the other question is, do we think there's a true business value for incorporating AI into the nuclear industry? And my answer to that is also a definite yes. Next slide, please. Just a bit about Sandia in terms of background. Sandia has a fundamental national security mission, including protection of radiological and nuclear materials for over 70 years. In this slide, we just highlight two classes here. this what we call Depot class and the ITC class, International Training. We teach security classes to all the agencies, and we also teach these classes internationally. In addition to the training, which is only a part of what we do design and deployment of security systems for DOE, DOD, and other U.S. agencies. We test and evaluate technologies, like some of the technologies that Tony referenced. And we also do R&D. And the DMA is one of the more recent innovations that have come out of Sandia's R&D effort. Next slide, please. Okay, so I wanted to acknowledge much of the DMA work is funded and supported by the Office of Nuclear Energy, DOE's Office of Nuclear Energy. There are primarily two program thrust areas, the Advanced Reactor Safeguards, ARS program, and also the Light Water Reactor Sustainability. And the work I think is made possible by their support for this. So I want to acknowledge and thank the program and program managers for their support. Next slide, please. Okay, so what's the problem that we're trying to solve? What's the problem we were trying to solve when we were thinking about the DMA kind of concept? There's a couple issues. There's two metrics you need for an intrusion detection system. You need to identify the ability to detect the bad guys come across. We use a probability of detection, PD, for that one. And the second part is the nuisance alarm rate, or the false positive rate for a sensor system. So that's when a bad guy doesn't come across your perimeter, but an alarm goes off anyway because of rain, because of wind, because of snow, because of animals. You have to have those two metrics to quantify. Many times, we focus on the detection part and we don't pay enough attention to the nuisance alarm part. And almost every vendor I've spoken with will never give me a nuisance alarm rate of their sensor technology. And most of my career, I spend going out to sites. I spent years on sites troubleshooting their sensors, and it's primarily because of the nuisance alarm rate they're getting. So that's one of the problems we're trying to solve. The other problem is intrusion detection systems are expensive. And we're trying to address those issues and see if we can't come up with new approaches to reduce the cost. So that's kind of the technical piece of the problem. There's also kind of a cultural piece of the problem that I'm going to introduce. And if the second kind of major bullet there is I say architecture for the perimeter intrusion detection systems have not really changed in 50 years. We're using the same architecture for the past 50 years in spite of the computational capabilities that have increased by more than a factor of 10 to the 7th via Moore's law. The cost of new sensor capabilities have dramatically decreased because, and they're driven by smartphone technology and autonomous navigation. So I see cost of sensors coming down, our computational capabilities going up, the size of our processors are going down, and then this has enabled new advances in artificial intelligence. And this is the area that I've kind of focusing my efforts on, is the artificial intelligence of this. And I have a quote. This is in 2008, this gentleman said that the computer in your cell phone is 1,000,000 times cheaper. I can't read that, so I'm looking back here. It's 1,000,000 times cheaper and 1,000 times more powerful. And about 100,000 times smaller than the computer at MIT in 1965, resulting in about a billion-fold increase in computational capability per unit dollar. So why do I introduce this on this slide? So I was saying, what's part of the problem we're trying to address? So there's a technical part of the problem, there's a cost part of the problem, and there's a cultural part of the problem. So even though we've had these huge advances in security technology, so why don't we see this being reflected in our new perimeter designs? Well, we hope to take a stab at that and make some progress on that problem. Next slide. Okay. So what is DMA? DMA is a sensor fusion algorithm that fuses multiple sensors to create a hybrid multi-physics sensor system. It explicitly implements this concept of complementary sensor phenomenology. That's where you have the strength of one sensor augments the weakness of another sensor. So if I have two sensors that are protecting a zone, it also forces the bad guy to defeat 2 sensors at the same time. I also use those 2 sensors to reduce my nuisance alarm rate. Let's see. It uses also a concept we call deliberate motion, where it pulls out the deliberate motion of an intruder coming towards us, and we believe we can differentiate that deliberate motion between alarms caused by weather, by foliage, and a little bit for animals, although we have more work to do on that. So the 2 images on the bottom, let's see here. So the image on the left, this is an actual screenshot of a radar system we were testing. We were doing some drone testing. And this is a result of about 10 minutes during a light rain doing this drone testing. And if you were the CAS operator, the central alarm station operator, can you pick out the intruder that's in the one on the left? And so this is the vision, this is the objective of what DMA tries to do. We try to go from this to this. And so there's only one of these intruders in here that actually have this track, and it's advancing towards our site. So this is the vision that we're trying to accomplish. And I believe because of this, it's going to enable new approaches to security technology. We're going to introduce one, but I think there'll be other things that it will make advances in. Next slide, please. Okay, DMA action. So let me show you a little bit what you're looking at here. This is a test bed here. The blue dots are actual alarm points from a radar. The yellow dots are alarm points from a thermal radar. And we did a sensor fusion of both of these radars. I don't show the fused dots, but we did a fusion of both of these sensors to produce our fused sensor system. Here is this GUI just shows the alarm status. So let's go ahead and run the video, please. Okay, so what you see here is the intruder is walking along. This is the outer fence. This is the inner fence. So this would be the unsecure side. This is the secure side in this hypothetical situation. And we see the walker. He's walking along the outer fence. It says, hey, I'm happy. There's no alarm here. We're tracking him. We're actually tracking all these dots out here. As soon as he turned to the left, and we asked him to move towards what I call the high side, the secure side of our test bed, we alarmed. And so what I wanted to show here is that DMA does track all these points out here. We had alarm points inside the PIDUS. We had alarm points inside our secure area. We had alarm points outside our secure area. We actually had alarm points inside and walking parallel to the fence. But it didn't alarm until we actually showed deliberate motion towards our high side. So that's kind of a vision about an example of how DMA works. Next slide, please. Next slide. There you go. So what you're seeing here, I'm going to show you a time-lapse video of a storm that of data we collected. In this example, I'm fusing radar and video analytics. I chose radar and video analytics because, one, they have high sensitivity, but they both have the issue of high nuisance alarms. So if I can solve the problem, or we can solve the problem with the nuisance alarm issue, then we can use these really high-powered sensors. Okay, go ahead and run the video. Okay, so what you're seeing here in our test bed, you see tumbleweeds that are moving out here, heavy rain, and you see raindrops coming across the lens. That will drive video analytics crazy. You'll get tons of nuisance alarms from this. You'll also see, after the rain, you'll see dry spots start to form in the rocks. That would also cause nuisance alarms from the video analytics, and of course these drops. And then we'll see some clouds come across. That's also kind of a pathological problem that video analytics has not solved yet by itself. So in this storm, during that day, we got over 5,000 alarms from the raw radar and the raw video analytics. And when we ran this through our DMA filter, we got 0 nuisance alarms. Again, this is just an example of the power of the deliberate motion analytics. Next slide, please. Okay, so I tried to give you a little bit about how DMA works. Now I'm going to give you some examples of test results in different environments. This first environment is just a typical 2-fence environment. In this case, my fences, come on. Okay. In this case, my fences are 60 feet apart compared to the typical 30-foot perimeter design. I show a runner with video analytics. I show a crawler with video analytics, and this is during the daytime. And we did some testing at night actually did it during heavy rain with hands and knee crawler and belly crawlers. So high-level summary of this performance in this environment. We had no missed detections. We're looking at runners, walkers, crawlers, and belly crawlers. We did over 140 tests, detection tests with 0 misses. We collected nuisance alarms for about a 6-month period in this environment from July to December, and that went through Sandia's or Albuquerque's monsoon season. And over a 6-month period, we declared 1 false positive, 1 nuisance alarm in 6 months. But yeah, we had no missed detection. Remember, to quantify an intrusion detection system, you have to have the detection part and the nuisance alarm rate part together. Okay, next slide, please. This is the second example of an environment that we tested DMA in, and this is in a beyond the fence. What I'm showing here is kind of a typical perimeter at one of our nuclear sites. I set up just a 100-meter zone out here. I'm using radar, and I have 2 camera towers. And let's see, this is just to give you kind of a feel for what the environment looks like. There's like 2 to 3 foot undulations in the terrain out here. The grass is probably 6 to 12 inches tall, dry grass, and we had some bushes out here. This is a sensor we used, the FLIR radar, and we had a thermal imager and a PTZ. So we ran, in this case, I'm fusing video analytics with radar. Next slide, please. Okay, the results. In this environment, this is a beyond the fence, unengineered terrain. We had no missed detections when I combined the 2 sensors. When I fused the 2 sensors together, I had no missed detections. We ran over 140 tests for walkers, runners, crawlers, belly crawlers, even belly crawlers in the grass. We found the video analytics had a really hard time with nuisance alarms, and it had a hard time with detection, but the radar complemented the video analytics weaknesses in this example. We only collected nuisance alarm data for 28 hours, but in the 28-hour period, we declared over 150,000 nuisance alarms in about a day. And when we ran it through the DMA filter, we had no nuisance alarms. Next slide, please. Let's see. We also did some testing, and I have permission from the folks at DC Cook to share this. So DC Cook Nuclear Power Plant is on the bottom tip of Lake Michigan. We were out there last year, February, March timeframe. We saw cold temperatures, cold enough where the diesel froze in our generator. So we think it got down to like -14, -15 kind of. We wanted to see how the DMA and the sensors would work in this really cold environment. And you can see here on this picture here, this tape it's not blowing sideways, it's actually blowing up. I mean, that tells you how fast the wind was blowing. I'm guessing it was probably 50 miles an hour. They said it was like 30, there's no way. On that lake, it was like 50 miles an hour. And you can see the waves here from Lake Michigan. When the wind would blow out, the shoreline would move back like 30 or 40 feet. And when the wind would blow in, you could see how far the shoreline came up, because would come up and freeze. And so here was a cone we stuck up at, and sometimes that cone was underwater, and sometimes the cone. So this was kind of the edge of our detection zone. Kind of to summarize our performance, I didn't count on this moving shoreline when I set this up. And so when we had a really narrow detection zone, my radar wasn't fast enough detected, so we didn't do very good on the runners. But we did good, so we detected the walkers and crawlers and belly crawlers with no misses. And this is also interesting. So we collected data out there for a 61-hour period. We had thousands to hundreds of thousands of alarms from waves, from weather, from rain, from snow, from wind. We got 0 nuisance alarms over the 61-hour period from weather, from the weather and the waves. And we did get 3 nuisance alarms from, they had like little herds of deer would come out, they'd drink water, and even they would come out, they'd walk around, we're tracking them and stuff, but they didn't have the same motion. There's some interesting features of that performance. I don't have time to go into them, but there's some really interesting things that I won't talk about. Next slide, please. One of the significant things of this test on the Lake Michigan is I think we have demonstrated a viable solution for the land-water interface problem that I would say to date has been a largely unsolved problem. So this is really encouraging results. Our last example is we tested out at Waterford 3 nuclear power plant in Louisiana. We went out there in August intentionally to capture the hot, humid, not so good on the testers, but the hot, humid, and rainy part of the season. Here's an example of the detection zone. This is about a 250 meter span here. We had our radar here, and we had pan-tilt zoom cameras that when we would declare an alarm, we would zoom to the cause of the alarm. This picture here just shows kind of the structured testing that we did. Every 20 meters, we did walk, runs, crawls, belly crawls. I say belly crawls. We actually used this aluminum ball to simulate a belly crawler. It's the same ball that you would use in your microwave systems. And so we're simulating a belly crawl. We're detecting them hundreds of meters out, and we're consistently getting detection. High-level summary of performance. We had no missed detections for walkers, runners, crawlers, belly crawlers, where the radar could see. There were places where the radar could not see behind buildings, behind towers, behind piles of gravel and stuff where we couldn't detect because the radar couldn't see them. But everywhere the radar had coverage, we had perfect detection. In the 15-day period, we had alarms from, I don't know, thousands, maybe hundreds of thousands of alarms from the rain. And that was one of the things we wanted to test. When we ran it through our DMA filter, we got 0 nuisance alarms from weather or rain. We did get about 1 nuisance alarm per day from, they had these big birds out there that I hadn't anticipated. They call them egrets or heron. And they would actually fly in like a drone. They would fly into our detection zone and then land, and we would declare alarms on those. Anyway, so we probably had, what was it? We had hundreds of alarms from the birds, but we declared about 1 nuisance alarm per day. So I say that this would meet DOE's requirements for a nuisance alarm and detection within the 2 fence perimeter, and we're getting good enough detection beyond the fence between their perimeter fence and their SOCA, the security owner-controlled area fence line, between their SOCA fence line here and their perimeters back here. And so this, again, is in an uncontrolled, unengineered area. So I hope that I showed a few examples of how DMA has worked. Next slide. How am I doing for time? Okay. Okay, so this is the so what part of the discussion. So why is this important to us? Well, I think that we've shown that it has some interesting performance, it has viable performance in these different environments. What I show here is a traditional security design. It has an inner fence line of 400 meters. And I have an outer fence, I have an inner fence. I have 17 sectors, 34 microwaves, 17 cameras, 8 field distribution boxes. These are actually more expensive than you might think. 48 lights and light poles, and I have to run power to these light poles, trenching and power for comms. So I show my central alarm station here, and notionally I show power and comms coming out to the perimeter and going around. You wouldn't actually do it this way, but for this notional example, this is how I'm showing it. And we have security fences, inner and outer. So this is the new architecture that I'm proposing, that we are proposing at Sandia to replace this traditional. We call it the DMA-enabled perimeter intrusion detection system. We're calling it DPIDS. So it has a radar in the middle. My radar can go out to 700 meters. I'm only going out, in this case, I'm going out 240 meters. So it has good detection. My pan-tilt zoom is a pan-tilt zoom bispectral, so it does thermal and visible wavelength at the same time. So I can do day-night imaging. When I get my alarm, I can slew to the alarm, the cause of the alarm, whether it's an intruder or it's a coyote or whatever. In this design, we have no sectors. We have no FDBs, no field distribution boxes on the perimeter. We have no lights or no light poles. It doesn't require trenching or power or comms. We have an 8-foot security fence. We have an outer fence. I do have a 40-foot clear zone here. So from my outer fence to my inner property protection boundary is 40 meters here. And I do that because of this radar is slow. It's 1 second to go around. They have radars that are faster, like 10, you can do it 10 times a second. This is an older radar that I used. And so what we're proposing is, in our estimates, is this: the new DPIS design is estimated to cost 40% less than the traditional design. So I believe that we can actually give better detection, lower nuisance alarm rate at about half the cost. Because of this, I believe that the DMA concept is going to be the way we do security in the future. Next slide, please. So I wanted to show you, so we have this, this RPM, this radar pan tilt zoom module, I call these RPMs, and I'm showing that I think this is a modular design. So we could use this to apply to larger larger footprints. And I show 1 kilometer by 2 kilometers. We could do 2 kilometers by 4 kilometers. So I'm just wanting to show, I think this is a modular concept that we can apply to larger sites. The previous slide was an example of a design for an ASMR, for a small modular reactor. We're actually building that test bed right now, and I expect to start testing to see if we get comparable results under one of the DOE programs. Next slide, please. Okay, so what's next? Okay, I already mentioned, so these pictures here kind of show where we're going with the DMA right now. We're building this test bed for this new DPIS design that I think we're going to get reduced costs, and I'll be producing a report probably by the end of the year on what performance is. We're going to do typical testing like the walks, crawls, runs. We're also going to do some challenge testing, so I'm just kind of opening it up to people that want to come out and try to defeat it. We'll have so this would be like multi-sector, multi-intruders at the same time, so we might have 2 teams coming in from the left and right, or the top and bottom, or maybe 4 teams coming in, 1 from each corner, 1 each side at the same time. Let's see. This picture here talks, we're fusing a radar and a passive RF system for drone detection. And we expect to complete that in the next few months to show that we can actually fuse 2 sensors to improve detection for drones and decrease nuisance alarm rate. They have nuisance alarm rate in these drone detections. Like I showed in that previous slide, I probably got 100 nuisance alarms during a light rain for drone detection. This middle picture here, you may not recognize it. This is a Garmin fish finder. This is a low-cost sonar. So this is actually a 3-dimensional sonar. It's pretty impressive technology, and I'm trying to incorporate this for a swimmer detection system for water intakes. What we're looking at doing is fusing video analytics on top, the sonar from the bottom. So if the bad guy comes in horizontal, I'll catch him with a video. If he comes in vertically and trying just to only expose maybe his head or part of his head, I'll catch him with a sonar. This is this complementary nature of the 2 sensors. So the sonar is one of the things we're hoping to actually show and demonstrate this year. And I'm looking for less expensive radars that are faster, and I'm also looking at incorporating LiDAR into my next sensor for to improve detection and also, again, decrease costs. So I think that's it. Questions? Oh, thank you, Greg.
No problem. All right, thank you, JR. So now we'll move on to Ronnie. Ronnie, over to you.
Good morning. Can everybody hear me?
Yes.
You got to hold it kind of close to your face, apparently.
I think this is my 4th RIC presentation, but my first as an invited guest speaker. And so appreciate the invitation to provide an NGO perspective. So thank you, Greg, for having me, and it's good to see you again. Slide 2. The Breakthrough Institute does not receive funding from the industry. We believe new and advanced reactors offer critical pathways to deep decarbonization, and we advocate for appropriate regulation in their licensing and oversight. Next slide, please. The first and last messages are particularly relevant to not only this RIC session, but also this conference. As Director General Grossi and NRC commissioners have noted this week, nuclear energy is crucial to public health and safety, and the regulator's mission is to enable the safe civilian use of nuclear materials. However, some current staff positions and practices present legacy challenges for the next generation. Therefore, putting the reasonable back into nuclear security is key to NRC's success. Next slide, please. Many forms of energy emit carbon, adversely affect human health, and propagate climate change. By contrast, nuclear energy is green and reliable. Timely deployment of safe and economically viable reactors is an urgent public interest. As others have noted this week, enabling the safe civilian use of nuclear materials is not promotional. Rather, it is a much overlooked yet vital component of the NRC's mission. The Atomic Energy Act of 1954 declared, "Atomic energy shall improve the general welfare, increase the standard of living, and strengthen free competition in private enterprise." The Energy Reorganization Act of 1974 reiterated this role to increase the productivity of the national economy, strengthen international trade, make the nation self-sufficient in energy, restore, protect, and enhance environmental quality, and assure public health and safety. Slide 5, please. The NRC has long been reactive, risk-averse, and resistant to change. I can say that because I worked there for 30 years. Today, the agency is under close scrutiny by Congress, the public, and other stakeholders who demand reforms and modernization. Deja vu. 25 years ago, Congress threatened to deeply cut the NRC's budget unless it modernized its inspection and oversight regimes. NRC insiders like me call this the near-death experience. In 2000, when I was a resident inspector at Catawba Nuclear Station, NRC implemented a new reactor oversight process, the ROP, which is performance-based, meaning the level of oversight is determined by performance, and risk-informed, meaning resources are applied to things most important to safety. Before the ROP, NRC had been testing safeguards contingency responses since 1982. In the 1990s, Operational Safeguards Response Evaluations, or OSREs, were conducted every 7 or 8 years as a main feature of the NRC's counterterrorism inspection program. I supported an OSRE when I was an inspector at Catawba. Much like today's force-on-force inspections or exercises, OSREs employed mock adversary attacks to test each site's physical security plan and defense capabilities. Check this out. In 1998, the NRC's counterterrorism program consisted of 3 qualified inspectors in headquarters, which was 0.1% of NRC's total staff in 1998, with assistance from contractors at $90,000 per year. The OSRE program was highly efficient and effective in revealing deficiencies, which licensees promptly corrected. By 2000, an OSRE had been conducted at every U.S. commercial reactor, and the NRC was seeking efficiencies under the new ROP. The following year brought 9/11 and reversed any efficiencies gained. NRC issued adversaries and orders to assess vulnerabilities and strengthen defenses against a new adversary. In April 2002, the NRC established the Office of Nuclear Security and Incident Response, INSIR, staffed it with former military and law enforcement personnel, very capable, and dispatched these new recruits to the field before properly schooling them in the regulatory craft, sowing the seeds of a hyper-vigilant regulatory posture. Today, INSIR includes 2 security divisions, 7 branches, and additional contractor support. Next slide, please. To satisfy the Nuclear Energy Innovation and Modernization Act of 2019, or NEMA, regulations must be risk-informed and performance-based as defined in the Staff Requirements Memorandum for SECI 98-144, and produce right-sized licensing reviews, a culture of realism, and regulatory discipline. Stacy, Tony, and JR have described important policy and really cool technology developments. Some are listed on this slide. I won't repeat them here, but I do encourage the NRC to consider more realistic, prompt response times and site-specific applications of RAPT. Next slide, please. I want to focus on the legacy of current regulatory positions and practices that will continue if they are not corrected today. Front and center is the perpetuation of high assurance in proposed regulations and guidance, which has the very real potential to impose undue regulatory burden. Why? Because 7 references to high assurance in Part 73 have long been cited as basis for far-fetched force-on-force exercise scenarios, protracted inspections that translate to excessive inspection fees, and inflated significance of performance issues. These practices and positions represent a long-standing culture of win versus lose and us versus them. Inspections are not competitions. Treating them as such can lead to arbitrary exercise outcomes. In 2016, the Commission took steps to normalize INSIR's culture by writing, in developing new regulations, the staff should be mindful that high assurance is equivalent to reasonable assurance. The NRC should eliminate ambiguity on this point. Contrary to this explicit direction, NRC staff perpetuates a high assurance standard for currently operating plants and for those of the future. Next slide, please. For example, high assurance appears in SECI 18-0076. A footnote reiterates the Commission's 2016 clarification that reasonable assurance is the standard, but the footnote is in reverse. The correct standard belongs in the narrative of the SECI paper, and the Commission's 2016 direction could be explained in a footnote. Last year, the Breakthrough Institute and American Nuclear Society objected to high assurance in proposed Part 73 language for advanced reactors. Recent changes have been partially responsive, but Section 73-100 now states the licensee's physical protection program provides high assurance of adequate protection. I'm throwing the flag, false start. High assurance also appears in guidance for operating reactors that will apply to future reactors once they are commissioned. For example, a risk governing access authorization cites high assurance with the inverted footnote to clarify purported regulatory requirements and impose an unanalyzed backfit. In February 2020, the NRC issued EGM 2020-01 to offer enforcement discretion for alleged non-compliances because its access authorization inspection procedure lacked clear and objective criteria. The EGM was based on, quote, investigations into potential violations of NRC regulations and associated wrongdoing by licensees, end quote. The inspection procedure's silence on this issue appears to confirm that the EGM and the RIS represent a new NRC staff position. Meanwhile, the industry, and ultimately the rate-paying public, have been billed for this regulatory churn and ratcheting since at least 2020. To date, no violations have been cited by the NRC, and only potential violations were investigated, which raises another question. Why did NRC investigate wrongdoing, presumably willful violations of NRC requirements, if no violations were identified? In another example, the recently released Reg Guide 5.71 pertaining to cybersecurity includes over 40 references to high assurance. Reasonable assurance appears 3 times, once in the background section and twice in an inverted footnote. Next slide, please. Footnotes get dropped, context is lost, and a high assurance standard remains. This practice defies the letter and the spirit of Commission direction, and it cannot be legitimized by a footnote. Why is the NRC staff so wedded to high assurance? Because it justifies a regulatory culture, positions, and practices. These institutional matters warrant correction today, and certainly before the NRC contemplates rulemaking based on oblique speculation about the security and accounting of advanced fuels and nuclear materials. The solution is to correct the high assurance language during the limited Part 73 limited scope rule change that's in progress. The regulatory basis for this change already exists in the SRM Prosecchi 160073. Legislation requires force-on-force exercises every 3 years, and the program has ballooned way beyond its efficient and effective predecessor, the OSREs. Congress should reduce exercise frequency in a risk-informed manner, and in the interim, NRC's leadership should proactively restructure and right-size a legacy empire. The Commission also has a role to play. The efficiency principle of good regulation states regulatory activities should be consistent with the degree of risk reduction they achieve. Where several effective alternatives are available, the option which minimizes the use of resources should be adopted. In 2019, the NRC staff appropriately recommended discontinuation of rulemaking to codify post-9/11 orders governing special nuclear material. Why? Because the effort would not improve public health and safety or security and is not cost justified. 2 years later, however, the Commission rejected this recommendation and called for further analysis. Who pays? The public. In conclusion, I applaud the NRC's openness to innovations, and we've seen some really cool opportunities to leverage technology for future reactors. However, for the nuclear energy industry to improve the public's general welfare, it must be economically viable, and some of these technologies, I think, will help with that. But regulatory practices present operational realities that could upend deployment. Putting the reasonable back into security for currently operating reactors enables the next generation to reduce carbon emissions, enhance environmental quality, and protect public health and safety. Thank you.
Thank you, Ronnie. I'll turn things over to Margaret now.
Thanks. All right, how's my sound? Good. Hi, I'm Margaret Ellenson. I work for Kairos Power. I am the Safeguards and Security Manager for Nuclear Facilities. Today, I'm going to be giving some of Kairos Power's perspectives on advanced reactor security. Next, please. Kairos is a mission-centered organization. Our mission is to enable the world's transition to clean energy with the ultimate goal of dramatically improving people's quality of life while protecting the environment. This mission is central to our work at Kairos to deliver clean energy that is both safe and affordable. Next one. I think I need one more. Great. I wanted to start a little bit with who is Kairos Power. We've been around for about 6 years now. We just celebrated our 6-year anniversary. Our work is to design, license, and provide physical demonstration for what we call a KPFHR. I'll spell that out for you. That is a Kairos Power fluoride salt-cooled high-temperature reactor. I'll refer to it as KPFHR going forward. We have established cost targets for a KPFHR power reactor that are competitive with natural gas in the U.S. electricity market. And to achieve that, we are using a rapid iteration design and development model and building vertical integration through in-house manufacturing capabilities. All of this, at the end of the day, will establish cost certainty for a KPFHR in both construction and operations. Next, please. So a little bit about Kairos Power's iterative development strategy. In each iteration, we use a plan, design, build, test, iterative loop. Each of these loops has a specific risk reduction objective, and each loop will progress risk reduction throughout the development cycle. We use a combination of non-nuclear and nuclear iterations. Non-nuclear is especially useful to be able to rapidly iterate on technology development. Our nuclear demonstrations are particularly useful for us to be able to demonstrate cost certainty that we're able to deliver in a regulated environment at target costs. This iteration strategy is also key for security by design. We're able to use the iterative loops to be able to mature and safeguards and security technologies and design, and also be able to use those loops and the time that we have with that to develop new security solutions. Again, all of this will be able to contribute to what you're probably all very familiar with the extreme, or I would say excessive physical security costs that we are experiencing right now with existing fleets that did not have the benefit of the opportunity to design in security from the get-go. Next slide, please. Okay, so drilling down a little bit more about how Kairos Power will be implementing security by design. We're using a combination of inherent safety features and technology development to realize opportunities to minimize operational costs while maintaining performance objectives. So how are we actually going to realize those opportunities? There's a number of things listed on this slide. It might be a bit of an eye chart for you, but probably pretty familiar to many of those in the audience. We're going to integrate design, safety analysis, security, modeling throughout the design. again, to be able to inform our decision-making along the way through our iterative loops. We're using those iterative loops, again, to be able to establish cost certainty for the final product. We have an opportunity for technology development of physical security solutions that are aligned with KP's mission. We're integrating security and safety, which is especially important for international deployment. We'll use layered protections, one of the fundamental principles of security by design, and also life cycle planning. I wanted to kind of pick at that one a little bit for a moment. So if you may or may not be aware that advanced reactors will all have different objectives related to the lifetime of a reactor or the life cycle of a reactor. And by life cycle, I mean the full construction through decommissioning. If we can plan for security throughout that life cycle, we can reduce costs both through the construction phase, through the operations phase, and through decommissioning. So that's another element of security by design that we at Kairos are considering early. Lastly, we're engaging with the regulator and the rest of our advanced reactor community through our aligning on demonstration methods and objectives for physical security, and also supporting generic solutions like rulemakings that the NRC is engaged with. And I think we've heard about those already. I won't go into those anymore. Next one, please. If I wanted to summarize Kairos Power's perspectives on advanced reactor security, it would be the opportunities listed here. Security by design, technology development, our inherent safety features of advanced reactors present an opportunity to reduce reliance on armed response and fundamentally change our security strategies at nuclear power reactors. There's opportunities to credit inherent safety features using new demonstration methods. We have opportunities to integrate programs, again, achieving efficiencies in both security and safeguards. And that, again, as I mentioned before, will be particularly important for international deployment. We have the opportunity to support advanced reactor development writ large through engagement with the broader community and, as mentioned on this slide, the advanced reactor security rulemaking. And most central to Kairos's mission, we have the opportunity to use iteration to be able to demonstrate the final cost targets and to demonstrate construction and operating cost certainty. That's the end of my prepared remarks. Thank you very much. I look forward to the discussion.
Thanks, Margaret. So we're going to move into the Q&A session now. We only have about 10 minutes left, but we'll be available after the session if anybody has any additional questions we can't cover. So, Tony, you were the proud recipient of the most questions, I believe, so I'll start with you. I'll just ask the panelists to keep the responses brief if possible so we can get through as many as we can. So, Tony, the first XE100 plant will be built adjacent to an existing chemical manufacturing site. Are there any unique security challenges that may be associated with this type of deployment?
Of course, I mean, you got to consider, some of the vulnerabilities of the chemical facilities, and what kind of damage, collateral damage could happen in that type of attack. But we're confident that we'll be able to work through those.
Thanks, Tony. Let's see. JR, you were the second in line in terms of most questions, so I'll go to you next. What do you see as the biggest barriers in the U.S. nuclear industry to adopting the new technologies you discussed? And the question alluded to both for advanced reactors and possibly for existing light water reactors.
What was the biggest, what? I didn't hear that.
What is the biggest barrier in the U.S. to adopting those technologies?
So I think they're going to be cultural, the cultural barriers. So we've always done it this way. What kind of risk am I adopting by going to this new approach? And what I'm hoping is that we can produce a sufficient data package showing, hey, this is how this technology behaves in these environments, and a driving force, here's the cost savings, will help you pull it across these cultural resistance. But I think it's cultural is the biggest impediment to these new technologies.
Yeah.
Thanks, JR. Stacy, this next one is for you. Security technology is a rapidly growing field with new advancements every year. As a regulator, how does NRC stay agile and adaptable to avoid being a barrier to implementation of safe current technology?
All right, I'll answer this kind of today and then the future for when we have Part 53. So today, we realize things change all the time. Because of that, built into the current security requirements, and I think I talked about it briefly in my slide, 7355R, it does talk about that there's alternative ways that you can do stuff if you have a certain analysis. We have a bunch of reg guides out there today as ways to meet security requirements, and reg guides are only one way, so there are optional ways today if licensees find a different way to detect, or some of the different software that we talked about today, provide it to us and we will review it. And kind of the whole point of Part 53, especially for the security, is the flexibility there. It's kind of like a design your own physical protection program, and we would review it as we see it. So we're trying to, we realize there's an issue there, want to make sure we're flexible. A lot of new things are coming. I mean, I was in NRO when we had the Office of New Reactors, really excited about that, that new change. Didn't happen this time. We see all the SMRs coming, and this is exciting and new, and it looks like it's moving forward. So I think we're prepared and going in the right direction.
Thank you, Stacy. So this question is for Ronnie, and I'll add a caveat. Notwithstanding the use of high assurance versus reasonable assurance in the regulations, or I'm sorry, in the regulations, what are your perspectives on the various regulatory initiatives Stacy discussed? And I'm specifically talking about security for advanced reactors. So are we doing enough? What more should we be doing kind of tactically, notwithstanding the words high assurance versus reasonable assurance?
Yep.
Does that question make sense?
I think so.
Okay.
So to me, the largest impediment is this language and the continuous application of the language in written form, because if it's in writing, then it can lead to a conception that something is of a different assurance standard than what the legislation, the founding legislation of the NRC specifies, which is reasonable assurance. The things that Stacy has described and what I'm hearing from my contacts in the industry and in the NRC, and I have plenty of them, do encourage me. I do believe that the NRC is open to adapting, and so that is all good news. I'd like to see more indications of that mindset change today, though, because if that's not addressed today, it does pose some challenges for the future.
Okay, thank you, Ronnie. Margaret, can you give some examples of how iterative development will affect physical security strategies?
Sure. I think of it in terms of what you can do in a non-nuclear versus a nuclear environment. In a non-nuclear environment, you can do rapid testing of plant layout concepts, of construction factors, access controls, technology development. In a nuclear environment, you can use iteration to learn about detection strategies, what works best, what's most cost effective. You can also iterate again on plant layout. In that sense, you're looking also not just at protection strategies, but also ease of operations and emergency planning as well. You need to be able to evacuate staff sometimes. You can also iterate in a nuclear environment on access authorization programs, SGI capabilities, and for both nuclear and non-nuclear demonstrations, you can also demonstrate supply chain for security and safeguards technologies to be able to build up scalable capacity.
Thank you, Margaret. So the next question is for, I guess it could be either Tony or Margaret. I'll let you fight it out over who goes first. But, Stacy discussed some rulemaking activities underway at the NRC that impact security for advanced reactors. Can you provide your perspectives on those potential rules and whether X-Energy or Kairos will be using the flexibilities in those rules if they're approved?
Well, X-Energy would definitely be using the alternative security measures. Also, we're looking at possible exemptions. But yeah, I mean, it's a challenge. Like I said in the presentation, where they're giving us in the proposed new rule language, they're giving us leeway on the number of armed responders, whether they're armed, relying on local law enforcement. But in the same paragraph, they're asking us how to, if they don't show up, what's our contingency to meet those regulations. So, but absolutely.
Margaret, you want to add anything?
Sure. I would say for Kairos, we are definitely tracking those closely. I'm optimistic about some of the elements in it. I do think it is called a limited scope rulemaking. There are, I think, some things to work out on the back end about what will it take to prove that we can meet those new standards, and also be able to marry what the new standard will be to what the existing Part 73 requirements are. I think some of the elements that might make sense in a light water reactor environment don't necessarily translate to advanced reactor. For example, things like core damage for a continuously online refueled reactor that uses pebble fuel. Tying back to core damage, we have work to do to be able to say, how does that translate to an advanced reactor environment?
Thanks, Margaret. I think we have time for 2 more questions. I'll start with JR. This is a bit of a long one. The IDS you discussed showed no obstructions, indeed nothing other than the PTZ radar inside the protected area. How does the picture change when the protected area contains assets you're protecting, which obstruct the radar?
So that's a good question, and we're working on that. Right now, if I look at, let's say, for example, an ASMR construct, and we have our reactor buildings kind of centralized, we would put the radar and the PTZs on top, maybe 30 feet above the buildings, to give us line of sight 360 all the way around. So that's our proposed solution for that.
Okay, thank you. Let's see, I'll go to Ronnie for, I think this will be the last one. Do you see opportunities or approaches to risk-informed security regulations? And if you could provide examples for what you think that might be, like specific examples, that would be helpful.
Specific examples for advanced reactors, because the technologies are so specific and unique, I don't really have any specific examples to offer. I think it varies depending on which technology and what design security features are built into the plant. And so I don't have any specific examples, but I think just the overarching kind of approach to nuclear security needs to be realistic and based on performance, instead of prescriptive requirements. For example, an 8-hour wrap time, while it is a nice new development that was discussed during last year's RIC, 8 hours is still a pretty long time as a generic application, so site-specific applications of a more prompt, realistic response time, I think, should be considered by the NRC.
Okay, thanks, Ronnie. I will ask one more question. This is for Margaret. Do you have any reaction to concerns raised by the National Academy of Science about MCNA, material control and accountability, for reactors like Kairos with online refueling?
Ooh, that was a long report.
You have 2 minutes to
Yeah, I'm afraid I would not be able to do that justice in this panel.
So if whoever asked that question would like to talk to Margaret afterwards. more than
Exactly.
happy to
I think
jump
that
into
would
it.
require a bit more detailed discussion.
All right, thank you. All right, so that concludes our presentation. A reminder, we'll be available outside the room if anybody has any additional questions for us or would like to talk about anything you heard today. I'd like to thank our panelists. Very interesting presentation. I really appreciate all the effort you put in. I got a lot out of it personally, and I thank you. I also wanted to thank Brad Baxter and Jahari Moore, who helped us coordinate this session, and the audiovisual staff from the RIC, who helped us get all the videos and all that working, and Metallica and everything. So thanks to everybody for joining us.